So I'm Rachel. I'm a postdoc currently at the ESRF in Grenoble, France at ID32. And today I thought I would do just a brief introduction to the ESRF, the specialties of our beamline, and then discuss the possibilities of soft X-ray spectroscopy, XAS, dichroism, and then get into our focus, which is resonant inelastic X-ray scattering. Finally, I thought I would close with a case study, my personal pet project, as well as Marty's, which is epsilon iron oxide, which is a very difficult material to understand. And I think with RIXS, we start to get some unique insights. So I don't know where I'm standing relative to the camera. The ESRF.
Don't worry, because the lights are.
Okay. Perfect. So the ESRF has 19 member countries. Spain is one of them. We have 46 available beam lines to access. And as a member country, you're free to put in proposals and have financial support when you come and do an experiment. I would strongly recommend taking a look at the website and considering. We have a variety of techniques. So we have scattering, spectroscopy, as well as a range of imaging techniques. Most of these are high energy. We're a 6GeV fourth generation synchrotron. So we've recently upgraded 5 years ago. And we have access to very high energy experiments that cover a range of materials. So everything from biology to chemical applications, to fundamental physics, we can cover at a beamline somewhere. Now to access, we do a peer-reviewed beamline system. Our current next call for proposal is the 1st of March. I would recommend everybody, if you have any interest in doing an experiment at the ESRF, explore the website. There's webinars that have been put out by individual beamlines that give you a better idea of the techniques that are available, as well as the capabilities of the beamline. And please reach out to a beamline scientist. Often these websites are not terribly up to date. And so if you have an experiment that you think would be interesting, be it a different sample environment, application of pressure, different temperature range, activation with the laser, usually we can find a way to make it happen, but complicated experiments, novel experiments require discussion with beamline staff. And so the sooner you have an idea and communicate it, the more likely we can tell you if something is feasible or not. So that's my advertisement for the ESRF as a whole. Now, ID32 is located, if I can use a pointer, in this lovely offshoot building that was built. We're one of the longer beamlines, and we're also the only soft X-ray beamline specifically at the ESRF. I believe there's a CRG, which is associated with the ESRF, but not necessarily part of it. We have 2 beamline end stations, one dedicated solely to resonant inelastic X-ray scattering, and then a slightly more versatile station where we do X-ray absorption spectroscopy. Our X-rays fall between 400 and 1600 EV. This means that we're well suited for the L edges of transition metals, the M edges of rare earths, and we can also do K edges of nitrogen and oxygen. Our flux at low energies is not fantastic. We really were optimized for copper and above. So that's something to keep in mind if you want to plan an experiment with us. We do offer full polarization control, 100% practically circularly polarized, as well as linear vertical, horizontal, and any angle you would want in between. Our first X-ray end station I want to talk about is the XAS one. And this, we have a superconducting magnet shown in yellow. We have the option of 4 Tesla perpendicular to the beam, 9 Tesla along the beam, so we can do dichroism studies. There's a small high throughput spectrometer that I'll talk about a bit later, as well as our sample preparation environment, where we have chambers for depositing molecules, chamber for depositing metals. You can do STM, PEM, to check the in situ growth of materials. The idea is that if you have a delicate sample that you want to prepare on site and then transfer inside ultra-high vacuum for the experiment, we're capable of doing that. Our second end station, and this is the one that often shows up in any of the promotional materials for the ESRF, is the large RIXS spectrometer. This is an 11-meter long resonant inelastic scattering spectrometer. It does high resolution, momentum space resolved RIXS, and the option for polarimetry analysis. So again, I will cover the RIXS aspects a little bit more specific later, but we are one of the world leading experts in resonant inelastic X-ray scattering. So why do spectroscopy? Spectroscopy looks at the interaction between electromagnetic radiation and matter. Soft X-rays in particular are probing the transition metals, the rare earth valence, and we can look a little bit at the ligands. This means that we're incredibly well suited for the study of magnetic materials because magnetism really lies in the valence and unpaired electrons. In a standard X-ray absorption experiment, we produce a core hole, and then either the absorption of this core hole is measured directly through a transmission measurement, or we measure either Auger electrons or fluorescence that's produced in the decay process. We get information about the local environment of the atoms. So you can see there's a difference if we're talking about just an atom, one that's bound in a molecule, or what we often measure at ID32, which is solids. And the resulting spectra tends to be proportional to the density of states. So common things that we're looking at with absorption experiments is oxidation state. You can tell the oxidation state of a specific element based off of either the line shape, shifts in the resonant energy. It gives you information about how these atoms are bound. We can also get detailed information about the coordination and ligand field. So here I've shown an example where we have splitting from an octahedral structure with 2 discrete energy levels to a distorted structure where now we have 4. And the complexity of the measured XAS signal scales accordingly. Once we've collected the measurements, multiplet calculations, DFT simulations can be used to reproduce the spectra, and then you can obtain quantitative information about your system. So CRISPy, which is built on the Quanti framework, is just one of the codes that are available in order to do these simulations. Even more interesting to me in particular is the study of magnetic materials. And when we want to talk about magnetism, we have to talk about the spin of the electron. And this means that instead of having a single density of states, we have a splitting that appears between the majority band and the minority band. So this imbalance in spin produces the net magnetic moment. And so we end up having this split band where the majority band is mostly filled and the minority band is partially empty. The filling of the bands is determined by Fermi statistics, and this will give us a difference between, say, an antiferromagnet, where we have a smaller exchange splitting, or a ferri or a ferromagnet, where this splitting is significant. The filling of the bands is determined by Fermi, and the net magnetic moment comes from the difference in filling. We can use the polarization of light to probe these differences using X-ray magnetic circular dichroism, where we align the moments with a magnetic field along the propagation of the beam, and then we use circularly polarized light, which has an angular momentum, to excite into the empty hole states. In practice, what this means is we get a dichroism and a difference that shows because left polarized light, which has a negative orbital moment, will excite electrons differently than the bright polarized light. And we see the difference in the filling of the density of states as dichroism by measuring left and right polarized and taking the difference. So the intensity of the dichroism is proportional to the magnetic moment. Just like standard XAS, this is an element-specific technique, and it encodes the site and the bonding information as well. So for a case of a simple oxide, say magnetite, where you have trivalent and divalent iron, that's in both tetrahedral and octahedral coordination, you do see the shifts in the spectra, and you can identify the contributions of each site using XMCD versus something like XAS, where they're all positive magnitude, and so it's a little bit different, more difficult to separate. In general, XAS and XMCD fulfills most of our needs for studying magnetic materials, at least as a primary characterization. We can get element-specific information about the oxidation state, coordination, as well as the magnetism. And for that reason, it really remains a workhorse. So there are a number of sites in the world. You can go to a synchrotron and measure XAS and XMCD, and it really is a useful technique. But this is a technique that came up in the 90s, and in the past 20 years, there has been a push for further technical developments and the need to try to get more information out of materials using the tools we have available. And this is where resonant inelastic X-ray scattering comes in. So it has some of the properties. It's the same basic excitation as what we do with X-ray absorption spectroscopy, but what we're measuring and how we're detecting is quite different. And we think of RIXS as combining scattering and spectroscopy. So with scattering, we get a momentum transfer where we're exciting in a certain direction, and then we're measuring how the momentum has transferred throughout. This gives us spatial information. Versus spectroscopy, where we're looking more at energy loss and the interaction between the light and the material. RIXS is unique because we're able to resolve the excitations in momentum space. And this is useful for dynamic processes. So for something like a superconductor where you have a spin density wave or a charge density wave that is tightly tied to other macroscopic properties. And this is where RIXS shines. So I have on the right an example of what a RIXS spectrum looks like. I'm going to show on the left how these features are produced. So the most simple part is the elastic line. So we have a photon in that excites our core hole. The electron sits in a empty valence state, and then it drops right back down. So the total energy contributed to the system between the initial end state and the final end state is 0, and that shows up at 0 in our energy loss. Slightly more complicated, we have our excitation to that same empty state, but the electron that falls down is from a different orbital. And this leaves our final state in a slightly excited position. And we can measure the energy loss, which gives us the exact orbital spacing between these levels. Same process for the second feature where we excite up and it drops not from the higher EG orbital, but from a lower 22G. And we get, well, there's a delay here, this exchange coupling interaction. The final thing that I have shown in this mock spectra is where we have the excitation, but instead of the electron filling from the iron site, it's filling from a ligand. This tends to form larger bands. So instead of having very discrete localized energy loss, we have the overlap and the hybridization between, in this case, I'm modeling iron and oxygen. And instead of having, say, a 300 MeV discriminant full width half max, you have these bands that stretch multiple EV. The excitations that we measure depends on the energy scale that we're looking at, and it depends on the resolution of the instrument. So our high resolution instrument, where we can measure in the tens of MeV, we're sensitive to some phonons, magnons, and bimagnons. So this will be stretching from about 20 to 30 MeV up to 200. We can also measure the DD, so these are the orbital excitations, which are the 1 EV to 2 EV range, and then charge transfer features. Which excitations you're interested in will dictate which instrument you want to use and will really demand what resolution you need. So our experimental setup, I've shown this with a horizontal scattering plane initially. So we can choose the energy of the beam, the momentum that we're choosing, that we orient the sample to relative to the incoming beam, and the polarization. So the polarization here is sigma. And then we measure in the outgoing plane, the energy out. This, we measure the entire spectrum. We then choose, based off of how we position the spectrometer in the horizontal direction, which point in momentum space we want to look at. So we align the sample with the incoming beam, and then we align the spectrometer such that we can probe a particular point in Q space. So this would be standard scattering geometry. And then we have the option to measure the polarization of the outgoing beam. In the vertical, we have the incoming beam that strikes the sample. We focus the beam in the vertical, which helps determine our energy resolution. The beam then scatters away from the sample. This scattered beam is reflected off of a variable line-spaced grating, which is spherically shaped so that we can refocus the beam onto our detector. And just like a prism, we have essentially a white line, so mixed energy beam striking our grating. And then as it hits the grating, we're refocusing so that each energy is discriminated vertically in the plane. What this looks like on our detector is this. So we have a sharp feature, which is associated with our elastic line. There's a bit of a dip, and this was taken on our lower resolution grating. So that's actually the band gap of the material. And then we start to see the losses associated with the DDs and the interorbital transfer. It looks like white noise. But if we integrate it horizontally, we can see the elastic line appears. We have two DD excitations that are trapped in here. There's a PD excitation, and then there's a large band of charge transfer and fluorescence that sits behind everything. If we take those at various energies, we can use it to construct an energy-dependent RIXS map. If we take it at various Q points by rotating either the sample or the spectrometer, you can resolve a RIXS map in momentum space. So this is a very versatile technique. It helps if you know what you're looking for before you start measuring. So this is our workhorse. It's our large spectrometer. It's 11 meters long. It weighs about 6 tons, but we're able to have continuous rotation on it. It has a high resolving power, so we resolve about 30,000 times the incident energy. Copper, this means that we're looking at about 30 MeV resolution. tends to be a little bit better as we go to higher energies, and lower energies, we are often flux limited, and so we'll degrade the resolution so that we can have enough counts. It has a 4-circle goniometer inside the sample. Once we orient the sample, we have an automated matrix where you can rotate to any accessible point in Q space, and then we can rotate the spectrometer automatically as long as we interlock. And this means that we can have continuous rotation. It's scriptable. We can run a macro overnight where it's measuring different points. Polarization analysis is possible at this end station, and this is where we have an additional step. So instead of having the grading straight through to the detector, we include a polarimeter where we reflect and can do polarization analysis. This is useful if there's particular excitations, be it a magnon or a phonon, where you want to excite in horizontal and vertical polarization and see the difference. It can help discriminate where the peaks are coming from. We also have a smaller spectrometer. So this is our high throughput spectrometer compared to the 11-meter long scattering length. Here we only have about 2. This means that our resolving power is about 10 times less because the distance we have between our scattering grating and our detector is much smaller. So the separation we get between energies is much lower, but still reasonably good resolving power, 10 times worse than the other branch, but our flux is 10 times higher. So you can collect your spectrum much more quickly. It has a fixed scattering angle, so we cannot do the full momentum space maps, but it's within our magnet. And this gives the unique possibility of doing high field MCD or MLD RIXS. So if you have a magnetic material and you want to separate out what the excitations are, the dichroism of the different sites, the individual energy levels, we can do that at this branch. And this is a novel capability at ID32. We also have the option of a lower base temperature and a few more tricks in terms of sample environment that we can do here. So kind of an overall summary of RIXS. RIXS is nice because it's bulk sensitive. It's element specific. We can resolve in both energy and momentum space. And in a single measurement, you can get rich, detailed information about a variety of excitations. The downside of RIXS is energy resolution is not as good as neutrons. It's not as good as some of the optical techniques such as Raman, but it has its benefits. The RIXS cross-section is quite small. And this means that you need an extremely brilliant source. You need a lot of photons hitting your sample so that there's enough photons coming out of your sample to detect. Data analysis of RIXS spectra can be complex, and the theoretical models are still being developed. So overall turnaround time of a RIXS measurement from experiment to publication does tend to be slow. The more complementary techniques that you have coming into this sort of experiment, the better chances of success. In terms of recent developments, the improvements of and the introduction of 4th generation synchrotrons, so this is EBS, Sirius, I have one more listed, Max 4. There's a few more that are coming online and getting upgraded soon, has meant better beam stability, better beam coherence, and an improvement in the overall resolution. We're seeing sub 30 MeV on the soft X-rays, sub 100 MeV on the hard X-ray, which is very exciting. And then continual developments in terms of grading technologies, spectrometers, and polarization control. So RIXS is definitely still an area that's growing and developing. If you're interested in it as a technique, I would definitely give it a try. And now I'm going to switch to some actual science, so something a little bit less pedantic. And this is epsilon iron oxide. So I'm sure you've seen it, heard it at some talk here before. It's a metastable phase intermediate to gamma and alpha. It's orthorhombic structure and it has 4 different iron sites. All sites are nominally trivalent, which makes it more complicated when it comes to spectroscopy analysis. It has an incommensurate magnetic phase at low temperatures, and at high temperatures, it's a ferrimagnet with high coercivity. So 2 of the sites are distorted, compensated with antiferromagnetic coupling. We have a regular octahedral site and a tetrahedral site, which have an uncompensated magnetic moment that gives the whole material a net moment. We know based off of neutron experiments that have been performed that there's no structural change that happens between the ferrimagnetic phase and the incommensurate phase. Oh, I prepared this on a Mac and I knew one of these slides would be messed up. This is the one. Sadly, it's very messed up. So in the Mossbauer, we see that there's a significant change in the tetrahedral local site. There's a significant drop in the hyperfine field of the tetrahedral site. And this tells us that there is a change in electronic structure. I can show you the data after if anybody cares. So we went to our standard workhorse technique with XAS and XMCD to see if we could get any information about what's happening to the electronic structure. Because Mossbauer gives us the local environment. So we know that either the iron is changing or something on the iron-oxygen hybridization is changing. If we look at the XAS, this is done at 50 and 250 Kelvin. There aren't significant differences. And this is a little bit of a problem, because we know from the Mossbauer that you can't see that there are changes that should be visible. Now, the XMCD in particular is a little bit confusing because we only expect 2 sites to contribute, and we don't see a notable change in the XMCD. So we went to a more powerful technique with RIXS. So this is an iron L3 RIXS map of epsilon iron oxide. As I kind of discussed and broke down the steps before, we have an elastic line at 0 energy loss. There's vertical streaks that show up around the 1 to 2 EV range, which are orbital excitation. And then we have significant charge transfer. So these are horizontal bands that stretch across that reflect iron-oxygen hybridization, as well as fluorescence. The fluorescence I haven't discussed before, but we have the excitation of the core hole, not into the valence band, but into the continuum. And then the filling of the produced core hole from the valence band. And this gives us our characteristic X-ray. This is a little bit different than the other excitations where we had a fixed energy loss. Here, the energy emitted is constant. And so as we change the incident energy, it shows up as a diagonal streak across our spectrum. So we measured at 20 Kelvin and 150 Kelvin. So we're in the incommensurate structure on the left and in the ferrimagnetic structure on the right. And there are differences. It's terrible to spot the difference, but if we subtract the 2 maps, we can see that there's enhancement in purple of some regions and a reduction in intensity of others. So working left to right, we have pseudoelastic scattering that's enhanced below the resonant energy. I say pseudoelastic because our energy resolution is about 200 MeV on this branch, which means that we have both elastic, so 0 energy loss in our elastic line, as well as any other low energy excitation, anything less than 200 MeV. So buried in our elastic line, we have phonons, we have magnons, and we could even have a bimagnon. We know that something is changing. It's probably not the elastic. It's most likely related to phonons. We have small effects that show up on the DDs. They're very, very tiny, but there's 2 purple dots here as well as the purple one here where we have slight enhancement. This is consistent with what was measured with neutron scattering, where we don't see a change in structure. So the actual electronic structure, the orbital structure on the iron sites, isn't changing between 20 Kelvin and 150 Kelvin, consistent with what we've measured. What's been measured structurally, I should say. Where we do see changes are the increased charge transfer as a very broad band at 709 eV and 2 narrower bands that show up at 710.4 eV. Finally, we have reduced fluorescence, which means that the ties between the atomic core levels and the conduction valence band is reduced at higher temperatures compared to lower temperatures. This could be a sign of some sort of metal insulator transition and probably points to the need of some sort of transport measurements on this system. But the 2 that I'm going to focus on are the bands that are showing up on the charge transfer, because we would like to be able to relate this change back to what site is actually causing it. So we turn to RIXS MCD. These measurements were taken on the small spectrometer, so it's attached to the magnetic field. We know from the magnetic structure that only 2 sites should be contributing. And when we look at the RIXS MCD map, sure enough, we see that there's 1 site in red and 1 site in blue. And this reflects the anti-parallel coupling of spins. From the resonant DD excitations at 709.6, we attribute it to the tetrahedral site, and 711 eV to the regular octahedral site. This is consistent with what you would get with simulations where we have a sensitivity to the bond length, causing a shift in the white line of the individual XAS spectra. So how do we connect it back to the RIXS map? It's an even shift of about 600 MeV between where the DDs are resonant and where the charge transfer is most strongly changed. And so we can take these results and attribute it to stronger charge transfer, stronger hybridization of the tetrahedral site, as well as more discrete orbital overlap changes on the octahedral site. It seems that this is only affecting particular orbitals, and further information is going to have to be obtained using simulation. RIXS is still a little bit of a theoretical development in process, and so this is work to come right now. So our main conclusions from these experiments is that the iron crystal field doesn't change with temperature. The high anisotropy phase with the high coercivity originates from a change in the iron-oxygen hybridization, and the fitting and simulation of RIXS spectra will have to be used to produce a better model and better understand this system. Other topics that have been in the publications recently, superconducting cuprates, where we look at the formation of charge density waves as we go into the superconducting phase. We have altermagnetism, where we exploit both the dichrism and the spatial splitting between the 2 bands, as well as battery applications, where we track the charging cycle of the material. In this case, it was a comparison of a standard battery material versus a novel one that this group had done, and seeing how the oxygen charging changed. Overall, RIXS combines both scattering and spectroscopy. It gives the opportunity of providing insight into many different excitations as a single shot measurement. The experimental conditions can be optimized to match the scientific questions. Planning in advance is necessary, but RIXS is just one of many synchrotron-based techniques. So these are unique to these large-scale facilities, but they are open access. You can't put in a proposal if you're not aware that it exists. And so hopefully this gives a little bit of a teaser of what you can look for in other measurements. And so with that, I really have to thank my team at ID32. I thank Alessio, who did some of the analysis on this, Martí, who helped provide samples and invited me today, and I guess open the floor for any questions.
Thank you very much, Rachel. Yes, questions.
Thank you very much for the very pedagogical talk. I have a question regarding when you show in some of your slides the dependence on the incident energy of the different excitations. You see that there is a Florence-like signal in the charge transfer region,
Yes.
but also I observed that there is a fluorescence line in the region of DD transitions, right, between 1 and 2 electron volts. My question is, wouldn't we expect in DD transitions to have Raman-like excitations rather than fluorescence? And so what is the origin of this fluorescence-like dependence in this DD transition region?
So it's, here, I'll put up a map just so then we have something to talk about. There was faster ways of doing this. Okay.
Yeah. Here, for instance, yeah, in the region between 1 and 2 electron volts, there is this fluorescence a little bit lower in energy, maybe.
This
Yeah,
one?
this is
The one that's streaking across?
yeah, exactly. This. So in DD transitions, you have localized, in principle, localized transitions.
Yes.
Why are not we observing here in this? Is a curiosity. Why are we not observing a Raman-like excitation instead of fluorescence-like?
Okay. So this is one of the big questions about this material. In a normal material, you're absolutely right. It should be Raman-like. We should see clear vertical streaks that are running down from transitions. However, because the cross-section of the transition changes, it won't be a discrete line that shows up throughout the entire excitation region. Here we have a couple overlapping features. So I don't know if one of the other maps, apologies, I'm going the wrong direction. I'm just trying to see if one of the other experiments had a normal. No, these were all high energy and oxygen. Sorry. We would expect Raman-like transitions for the DD charge transfer as well as anything intraorbital. The problem with the maps that I showed is we have contributions from phonons and megons, and that's giving a bulge and a distortion onto the elastic line. One of the questions we have about this material is whether or not it's negative charge transfer. So what you're seeing in that region is the absence of a band gap. And this is very strange. At 100 Kelvin, it turns off and you have the clearer Raman-like excitations because this background of fluorescence does disappear as a function of temperature. Your expectations are right. It's the material that's not behaving. That helps.
Thank you.
Sorry.
Other questions?
Thank you for the very nice talk. I have another pedagogical question. Can you discuss again the physics of why there is a rigid shift between the DD transition? And it was one of your last slide. So I would appreciate. Thank you.
Sorry. I'm sorry.
I mean, your last slide, we have maybe before. Yes, at some point you show that you have excitation, but then there is this less than electron volt.
Yes.
The rigid shift. Now you show the lines.
Yeah, a constant shift. And this comes because we have the resonant excitation into the DDs, or where it's dropping down, it's associated with the cross section. It's one of those features that is known, but not terribly easy to attribute, unfortunately. Yeah, I'm sorry.
It's okay. Thank you.
It just appears that way. I would have to look further. I apologize.
More questions?
Thanks very much for the great presentation. I had a question actually about this graph you have here. So as I understand it, you subtract one spectrum from the other, the one at 20 from the one at 150. I was wondering why your elastic line is changing so much, because it seems a lot more intense, right, in the one spectrum. So I mean, when you're analyzing these data, how easy is it to decide kind of where you're supposed to judge what's positive and negative, let's say?
Yes. So these are all very processed data. So this is a powder sample. So even the amount of sample that's in the beam will change as a function of temperature. So we normalize these to the DD excitation. So there's one DD excitation that we associate with the regular octahedral site, and everything is normalized to that one point. We chose this because when we look at a film sample, which is much more homogeneous compared to the powder, we know that that DD doesn't change as a function of temperature. And so that's our normalization of intensity for both of the maps. The other thing that we have to be very careful, particularly for something like this, where we're subtracting maps, is any vertical energy shifts that could be happening because of shifts in the beamline. So processing of RIXS data is definitely non-trivial. It is intensity counts. So there's certain features that we would expect to change or not to change. So the fluorescence, when we take it with the two polarizations, we would expect not to have a significant difference. We can tell in the band gap region if there is a shading that shouldn't be there. So it's mostly paying attention to artifacts. In the elastic line, we can see that the difference between the edge, so this is where it really should be a pure elastic feature, there isn't a difference. So this is above the L3 edge, getting into the L2, and this ideally would be pure elastic compared to our quasi-elastic, where we have phonon and magnon contributions. And so the fact that that is going to 0 tells us that our normalization procedure and our processing is reasonable. But it also sets an idea of what the uncertainties are. So this has a very faint orange color, and this will kind of allow us to identify whether or not we think these are real or whether it's an artifact of the processing. RIXS maps are slow to collect. So these maps taken with full current still took over 4 hours, 4 to 5 hours. And so you have the time changes in the beamline in the sample that we need to consider as well. So it's complicated.
Thanks very much. I had a follow-up question on that, because it was, while you were talking about it, came into my mind, you were talking about powders and thin films. What's the spot size of the X-ray beam?
Right, so our spot size helps determine our resolution. At this end station, we have a 10 micron vertical spot size because we have a focus point on the sample, and then we reflect off the grating to a second focus point on the detector. If everything's perfectly aligned, our beam size on the sample helps determine our resolution. So it's 10 microns for the small spectrometer, the shorter scattering length. On our large spectrometer, it's 2 microns because we have a larger path length and then we have a larger scattering arm as well.
Great. Thanks very much.
So, no problem.
Okay. Very nice talk. These are the results from nanoparticles.
These are results. from-
Martí also has thin films.
I know.
Have you already worked with this, and there are difference between these nanoparticles and the thin films?
There's a little bit of a difference. Some of it, it's hard to tell whether or not it's due to geometry effects. Because if we have a powder, we're looking at a powder average. In a thin film, we can orient and we have the opportunity to do some sort of momentum space mapping. We see subtle differences, which modeling-wise, we can attribute to geometric effects. With the films, we didn't have the sign of the characteristic low temperature transition, and so we didn't do the low temperature measurement. In general, the most information you can get from RIXS will come from a single crystal, where you can really map out properly both momentum and energy transfer. As you go to a thin film, where it becomes a two-dimensional structure, you have less access geometrically. And then with the powder, you have the complication of a powder average. So when it comes to simulation, you would have to basically simulate every possible point in momentum space, and then every possible intermediate and final state. And so that's one of the reasons why we don't have models right now for.
And what about the surfaces? I mean, they might be very different, no?
Yes, so RIXS.
Accounted for.
So RIXS is bulk sensitive. So unlike XAS, where it's usually electron yield measurements and we're very sensitive to the surface, RIXS is more of a, it is a bulk probe, an inefficient bulk probe, but bulk.
Okay. Thanks.
Going between nanoparticles and films, we're going to have differences in strain as well, which could factor in.
Thanks. Just two questions. So you were able to see a change in the intensity of the charge transfer excitations at the tetrahedral site in this your first example. But do you think is there any chance to even after modeling to distinguish about the sign of the charge transfer band gap in the commensurate phase? If it's going to be, is there any chance to distinguish between positive or negative charge transfer in the commensurate?
Yes.
The second question is if there are any relevant difference between your beamline in Grenoble and the other one, the I-21 beamline in Diamond. If maybe you can make a comment if they are very similar or not.
Absolutely. So the direction of the charge transfer, whether or not it's positive or negative, we have the measurements, we have the analysis, and at 100 Kelvin, so this fluorescence line that was remarked on before, why there's no clear Raman-like excitations, that turns off at 100 Kelvin, and we can see that this fluorescence band extends all the way to the elastic line. And so there is no charge, there is no band gap, and that tells us that the high temperature state is most likely negative charge transfer. The low temperature state has some other features. We need to discuss that further. In terms of differences between the beamlines, so if you want to do a high resolution RIXS, there's ID32, there's the beamline, you mentioned at Diamond. There's one at NSLS, and there's Nanoterasu in Japan, also has a high resolution RIXS. The Swiss light source, in theory, has one as well, but they haven't come back after the upgrade. The design is very similar. Pretty much all of the RIXS beamlines, I think, have originated from the Milano team's design. And so that's kind of propagated throughout the world. Resolution is similar between all of them. User friendliness varies a little bit, and then the flux at the particular beamlines is different. So at Diamond, they have much, much better flux at low energies. So if you were in the market of doing, say, an oxygen edge experiment, I would absolutely send you their direction and not ours. Time matters for RIXS because it's photon hungry. And so the difference between our beamline, where it might take 6 hours, and theirs, where it would take 4 hours to get a spectrum, really makes a huge difference. Our beamline is slightly better in terms of the design of the spectrometer. So we have a special differential pumped shield on our sample space, which allows the continuous movement. So we don't have to stop the measurement and repump the vacuum. One of the downsides with working with soft X-rays is everything has to be measured in ultra high vacuum. So our beamline functionally is about 10 to the 8 to 10 to the minus 10 of millitorr of vacuum. If you have to stop and wait for pumping, it again eats into your experimental time. Nanoterasu, I should mention specifically, has reported the best resolution in the world for RIXS right now. So they're claiming 20 MeV on the copper L edge. We haven't seen any papers with actual measurements, but I think they're coming. Max 4 is a unique RIXS beamline. They're a soft beamline, but they focus on liquid measurements. So if you want to do a liquid jet measurement, you would go there. They have some technical issues regarding resolution, so I wouldn't recommend it for a solid state sample. And then there's also the option, I know the Swiss light source does pump probe RIXS. So if time resolved is of interest, FERCA beamline at Swissfel, as well as there's an XFEL beamline that will do pump probe. So kind of a rough comparison of the options.
I have one question myself. Can you comment a little bit more on the possibilities of using the high throughput for inoperando measurements in, I don't know, catalysis, electrocatalysis, and batteries?
So this is something that we're working on. Currently, there are no beamlines that have reported inoperando measurements of soft RIXS. We have a couple test experiments planned right now using solid electrolytes, where we're having promising results you can measure during the charging cycle. A lot of them have been charged. So the data I showed on the batteries, those were pre-charged and measured ex situ, but we have an inoperando cell in progress. We have facilities on site if you have catalysis materials where you can bring a reactor and then put it into vacuum. The ultra high vacuum is often a problem when we're dealing with in situ. We do have what we're calling a multiple property simultaneous measurement instrument where you can apply electric fields. You can do Hall probe measurements at the same time, strain measurements at the same time. So if there's a material that you're interested in that might be reacting with the X-rays, or you want to have another measurement system, electric gradients, thermal gradients, that sort, we have a lot more versatility on the high throughput. There is a sacrifice in terms of resolution. But if there's something that you want to try, reach out. We can probably find a way to make it happen if it hasn't already been done. We do have setups for strain measurements, specifically single crystals and thin films, both piezo-based as well as mechanical-based that we can do. Those tend to be complicated measurements.
Okay, Rachel will be here this afternoon and tomorrow.
Yeah.
So if anyone wants to talk to him, just tell me and we will organize that. So thank you very much.
Thank you.